And I'm presenting my end of semester project for CpSc 8520, which is a grad class in the Clemson Computer Science Master's Program. And the class is called Internet Working, and the project is called GIMServer, which stands for Global Internet Monitor. You're looking at one of the interfaces for the server, which is at a high level. It's used to track the performance of other interfaces in a network. But let's take a moment and talk about the motivation and the structure of what we have here. All right, so it's very common to set up a monitoring service to monitor some other IP address and port combination on the network. So let's say you have monitor M, and let's say that you have another some target T, and you just want to basically regularly ping T from M and track information such as the latency or the throughput of the connection, so on and so forth. And this works well. Now, if you want to get a little bit fancier, you might set up multiple monitors. So let's say we have M2, and M2 is also tracking T. Now, M2 might be perhaps just a redundancy measure for M, or perhaps it's actually located in a different location so that you can rule out, maybe M fails or has issues connecting for some reason related to congestion along this line, but M2 gets through. The point is you do get some additional guarantees by having M2 around. Now, what I've done is take this idea and generalized it so that you can have as many servers as you want. All right, and but the setup that I have here is that each of these servers is part of a distributed peer-to-peer network, which means that we can interact with any of the servers through a web interface, which I'll show you, and we can inform those servers about new targets to contact. And then the rest of the network will organically discover that we need to track that target as well, and then we'll be able to actually view ultimately the results of that monitoring side by side in real time. So just a quick demonstration of the concept, and then I will demo it to you live. Let's say that we have some setup here, for example, where we have this server is monitoring T2, and maybe these two servers have both been told to monitor T1. Now, what we would like is for these two servers to be able to automatically monitor T2, and for this server to be able to monitor T1. So how is that going to happen? Well, the first step is simple. When you launch a server, you have to tell it the identity of some upstream server that it can contact for more information about the peer-to-peer network. So in this case, let's say that's M1 is sort of the point of contact that everyone it knows about. So when these servers come online, M1 doesn't know about M3, but M3 does know about M1 because that could be M3 can be told about M1 in a variety of ways, and M2 maybe also is told about M1. Now, M3 and M2 do not know about each other yet, for instance. But the next step is M3 can contact M1 because it knows about it, and M1 can acknowledge that. So now M1 knows about M3, and we can establish through a little handshake relationship, basically a peer-to-peer connection. So now both of these servers know about each other because M3 reached out and M1 responded. And likewise, M2 can reach out to M1, and M1 can respond. But now what we have here is a situation where M1 knows about M3 and it knows about M2, but M2 and M3 don't know about each other. So M3 can query M1. It can query M1 for a list of the of peers which it might have, that's full peer list, which in fact this happens regularly. M3 queries M1 for that list of peers. M1 responds telling M3 that it knows about M2, and now M3 can reach out to M2, and then M2 can respond. We have a handshake, and now we've formed a full a connected peer-to-peer relationship. And if we wanted to, we can prune. If you had many, many nodes, they wouldn't all connect to each other. But the point is, there's automatically news about one of the nodes spreads around the network to the other nodes. Okay, so step one is to establish this peering relationship. Step two is to go from this peer relationship to now be able to get information about these targets. And this is actually very easy now that we have a peer relationship, because each of these nodes, the way I've set it up is every few seconds we'll query, they'll pick a random peer, so each of these now has 2 peers, so it'll pick a random peer and ask it for a list of its targets. And so the first time M3 asks M1 about its targets, it'll find about T1, and it can start tracking T1. And the first time M1 asks M3 about its targets, it'll find out about T2, and I can start tracking T2. And M2 now could find out about T2 from either M3 or M1. It really could be either. It just sort of depends on the timing of things. But within a few seconds and just a couple passes, M2 should know about, the entire network should know about all of the targets that we want to track. And you can actually work out by a little bit of math that it's almost logarithmic time. So if you have n nodes, it's very close to logarithmic time for all of the nodes to find out about all of the targets that we're interested in. Now, in this setup, what we've accomplished is something pretty interesting. We have a set of independent nodes that are each capable of monitoring nodes on their own, but then you can log on to any one of these servers. So let's say I decide I want to monitor T3. Well, I tell M3 about it. It starts monitoring, and then its peers will query M3. So M1 will query M3, or M2 will query M3. One of these will query it pretty soon, and one of those will find out about about T3, and then within a couple passes through the network, everybody's going to know about T3, and so now they can monitor it as well. And now we can easily compare the results of monitoring these together. Okay, now I'm going to demo to you the exact process that we just discussed in the setup that I've created. So first of all, here's GIMServer. So I'm running a local instance of it here. It's tracking various things. And just to understand this interface, we have this page targets, and it shows you a list of the targets that this instance is trying to track. We can enter new targets directly through the interface here. We can remove targets if we need to. And you can click on any one of these to see the result of tracking that target. I'm actually going to demo this on a public peer though. So this local instance is paired with some public instances. So I've deployed this service on 3 different AWS servers. Each one is in a different region of AWS, so they're in a different geographical region. So you have one in the US East, which is in Virginia. You have one in US West, which is in California, and you have one in EU West, which is in Ireland. So that gives us 3 very different perspectives on the performance of an API. They're going to go through different network paths. We'll just get different stories. And let's open one of these. So let's say we pick this one. So here's a server. It's a public instance. It's tracking some of these targets on its own automatically, and I want to tell it to track another one. So I can show you from beginning to end what happens when you start targeting one of these. So let's pick something that's not in any of the other servers, and just for fun, I'll go ahead and I'll open up some of these other peers. So we have one at this IP address ending in 19, one at this IP address ending in 113, and this IP address ending at 207. Okay, now I'm going to tell this guy about someone. Maybe I'll have it monitor. What's a good website that we're all interested? Maybe stackoverflow.com. All right, and we can either do a UDP ping if there's a UDP server running at that server, or we can just do an ICMP ping, plain old. And I think that's what we'll do in this case, because I don't know if Stack Overflow has a UDP echo server running. So I can go here and let's just find out real quick the IP address of Stack Overflow. All right, so we have this. All right, now I'm going to go here. I'm going to enter this IP address, and we'll give it a display name so we know what this is. And I'll give it a port number that doesn't really matter since it's going to be ICMP. It would matter more if it was UDP. And I'm going to click Add. Okay, now we've added this to the local database that this instance runs, and I'll talk about the internal architecture of each of these instances in a moment. But we have this guy, and if I click Track, you'll see that it's running. We've already succeeded in pinging, but what you'll also notice is very quickly the other two instances that this is paired with found out about this URL as well. So I have it set at a 5-second window, and so you can see within moments. So this happened at 12:02:42. So this is at 38. So within 4 seconds, this instance found out about this target we want to track, and within 5 seconds, this instance found out about the target we want to track. If I go here and refresh this page, we'll see that this guy has found out about Stack Overflow. He's tracking him. This guy is tracking Stack Overflow. He's tracking him. And because each of these servers is now tracking this IP address that we've entered with this protocol, they're each collecting data on it, which means that now we can actually compare them side by side. And so you'll notice that we're running on a particular server here, but it knows who its peers are, and it knows the peers' public API for getting the information about performance. And so it's just in real time, it's querying its own API, and it's querying its peers' API, so that we can see this side by side. And in this case, something that's pretty interesting is we have almost zero latency from this guy, 54, 193, 195, 19, which I believe that is US East 1. And what that tells you is that it's very likely that the Stack Overflow server is probably being run in basically the same data center. All right, so we get this very interesting relative information. You can see it very easily which one is closest. So very easily which one is closest. And this EU server, on the other hand, pinged that IP address, and it actually has better performance than this California West IP address. But probably what's most important about this is that you can see relative behavior of pings. Now you can see that this instance spiked. There was a ping spike at 12:04. And 38 seconds. But that was not experienced by either of the other two instances. So what that tells you is that we can really discount this one. So this wasn't real. Neither of these two spikes in latency actually are reflective of the true latency of this location. And you can see that when you do all three of these in aggregate, you get a very, very smooth trend with a really very minimal variation. And if we want to, now that we have a little more data, we can switch to a higher resolution window, say a 60-second window, which also means this won't refresh quite as often. And you can see you can see the difference where we've basically have a very consistent ping performance from these two endpoints, whereas this one has slightly increased in average latency. All right, and eventually we'll get more data here. And we just started this process monitoring this location, but as it turns out, I've already been monitoring some locations for a little bit longer than that. So let's pull up, say, one of the other peers. So actually, each of the peers also runs a UDP echo service, which means you can ping your other peers for latency as well, which sort of gives you the backbone of the service in terms of what you want to track. So I can go here. Let's say we go to this guy, and you can see after a second the results from the other peers come in, and let's aggregate maybe at a 30-minute window. And so going back to going back about 12 hours here in this connection, you can see that well, in this case, this is actually us pinging ourselves. So there's very low latency here, but again, you can see some of the natural variation. This should be, literally zero or about as close as you can get to it. But there's actually a spike here, which tells you underlying performance issues on the server, or maybe it tells you something about load. And then then these are much more noisy, and it's likely that they're much more reflective of intermediate network congestion. All right, so that's the heart of the project. We have a server that you can spin up on as many copies of it as you want. They link through a peer-to-peer network, and they automatically discover what the other servers are interested in, and we can track the results of performance monitoring from those servers side by side in real time automatically. And that was really the vision with this project. Let's talk now a bit about the internals of this setup. So I have a couple things to show you really quick. So first of all, each of these services, here's what it looks like internally. So I'm treating here's a yellow. This is meant to represent a instance of GIMServer, and these are meant to be other instances of GIMServer in yellow, but it's not in quite as much detail. So there's actually 4 processes that run. There are 4 processes that run inside the server, and I'm actually going to, let's make those purple to illustrate that these are services. I use the Unix's systemd setup so that these services will start up automatically and reboot, and they will, if they die through some accident, they'll be automatically restarted. So they're persistent services. There's 4 of these running within each of these instances, and what you have actually, hang on. Okay, we can do that. So what you have here is, first of all, you also have a database that's a SQLite database that powers all of this. So all of the services talk to it. The web service talks to it. Other external services might reach out to it. This is what holds all the magic together, and it's really cool how you can use such a simple, literally a light database to power all of this. It's quite performant, and even though it's handling even some parallelism in the requests, that's really neat to see. Here's what the services do. So the website that you see and the API that gives you access to the database from external sources is a Python Flask server, and it exposes through to port 80. So it's not HTTPS, but it's still a public website. Then we have sort of independently a UDP echo server, and that's really just for convenience to give you some things to ping. If you need some services at the outset to ping. So each one of these does expose a UDP echo server that you can ping. Then we have a couple other services that are running in loops. So first of all, you have the monitoring service, and the monitoring service takes the list of external services that the database, the targets the database knows that you want to talk to, which the website might give you some additional ones there, and it just regularly pings those services every few seconds and gives you an update on the performance there. And then you have the peering service, and the peering service looks at the list of peers that's in the database, and it goes to those peers and it talks to them. So every few seconds, it'll query a random peer to find out from it information about A, are there any new targets that we need to monitor, and B, are there any other peers? Because if there's any new peers, then we can reach out to them and establish a handshake and expand our network, which is how basically the propagation between these services work. So all of this lives on an instance. You can run it locally if you want, but it's really configured to be run on an AWS Linux instance, and that could be packaged up into a Docker image for convenience, and that's something that I would probably do if I was trying to make it really easy for other people to use this. So we have this, and you can see this is running in AWS. For example, if I go here to my console, my North California console, you can see I have one instance running in that region. And I can click on it, and I can connect to this server, and I can see what's happening on the server. So if I I can search the I can search for processes that are running. So in this case, you can see that there's a process that's running that handles the peering service, which is a Python file that's running a loop, and we have a Python file that's handling the monitoring service. All of these are maintained through Unix system services. And you're welcome to dig into the code and the structure more if you'd like in the accompanying paper. All I would say is that all of this is also open source. So I have this on a GitLab project that's publicly available, and all of this code is out there. You can read through it. You can see exactly what we're doing. For example, we have our web server is here with exposing various APIs, and our peering service that runs on a loop is here, so on and so forth. So in conclusion, this was a super interesting project. I learned a lot about setting up AWS services, particularly persistent and fail-safe AWS services, about internet monitoring, about creating web servers, creating a database, and that is one thing, by the way, that's a little bit nifty about this, is that all of this data goes into the database. That's why we're able to perform aggregation like this. So we're not parsing logs. We actually have this information in a database, which makes it easy to do some really powerful data aggregation techniques. And in the future, we could probably do some very interesting things built on top of this. Thank you so much for watching.